Today's topic is derivatives of inverse functions. So we'll add to our things that we're able to take derivatives of. So previously, remember that we've learned before that if we have a function and it's going to have an inverse function, it has to pass the horizontal line test. So we called that function one-to-one if it had a unique inverse function. So if we had an inverse that was a function, okay, so not just something that undoes sometimes, but always a unique inverse. All right, so basically definition of an inverse, and this is how we had to verify something was an inverse. We said that the function called g, in order to be the inverse of the function f, meant that if we did f of g of x, the answer was x when we simplified everything. And then if we did g of f of x, we also got x. And then we wrote it with that notation that, remember, we're sort of stuck with. And we read this f inverse. Do not read that f to the negative 1 ever, 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 ever. It's f inverse. So that's how we verified things were inverses. So basically it means that they each have to undo each other. You apply one function, then you apply the other one, you undo everything and get back to the x that you started with. So another thing that was really important, and this one's what we're going to use a lot today, is that the graph of f is, so if we have f and we have f inverse, so if f has AB on it, then f inverse has BA. So that was important. All the x's and y's were switched, and you should remember hearing that a lot. X's and y's are switched. Okay, so we're going to use this reflective property to fill in these tables, and then we're going to use it to answer some questions below that. So complete the table of values here on A for f inverse. So A has x and it has f inverse. So for f inverse of x, basically it means when you see these two values, they're going to be switched. So you're going to have 2, 3 instead of 3, 2. And for the next values, negative 1, 1 instead of 1, negative 1, and then 4, negative 1. And that's how we do it. That's what switches it. So we would do the exact same thing for g here. So again, you look at your x and your g of x, and then we're going to make this the x and this the y, or the g inverse. Okay, so basically you're switching x and y. So we do that for all the points, and we just switch them for the direction that we go. Okay. So now we go to C, and we want to find the value of f of g inverse of 0. So going back to the table here, we have to work, of course, we're doing f of g inverse of 0, so we go inside out. So first we need g inverse of 0. So that means right here, because we're going to plug in 0 as our x and get the value of g inverse, which is 1. So this is going to be f of 1, because g inverse of 0 is 1, and then f of 1, we go back to the table. So now we got to go to the original table, because we've got to do not f inverse but f, and so f of 1 would be negative 1. So this answer is negative 1. So same thing here on D, we want to do f inverse of f of negative 1. So back to our table, f of negative 1, so that's going to be, right here is negative 1, and we want f, so that's going to be 4. So that means we're doing f inverse of 4, and then we go back to our tables, and we see that f inverse, this is the table for f inverse, we want f inverse of 4, and that's going to be negative 1. Okay, which shouldn't be too surprising that we kind of we went back and forth and we got back to where we started, because we did f inverse of f of. Okay, next one, f inverse of g inverse of negative 1. So go back to g inverse of negative 1, and we get 3. So we're going to have F inverse of 3. And then we want to look at the F inverse table, F inverse of 3, and I don't have anything. I don't have an X value. I don't have that for this table. So we're going to have to say that this is undefined because I don't have a definition for F inverse of 3. Okay, so we're going to assume that this is like the entire function values that we have, then that's all we've got. All right, then we have G inverse of F inverse of 4. So again, we go back to F inverse. F inverse of 4 is on the bottom here. So we get -1. So this is G inverse of -1. And then we look at our table again for G inverse of -1. And we get that that is 3, looking at the bottom table there. So there's my answer. Okay. Now you can also consider that you kind of could go back and forth. You don't have to write the inverse as points like that, but it does help a lot if you'll do that. Okay, so again, a function has an inverse if and only if, and that means both directions are true here, it is 1 to 1. And 1 to 1 again means for every x, there's exactly 1 y, and for every y, there's exactly 1 x. So it's 1 to 1. And if you remember, we used the pop machine example, and to think about that. And the only way that you would know if there was a can of pop left in the, somebody paid for it and left it there, you don't know what button they pushed unless there's only one button for every different kind of pop. There's not 2 things. So 1 to 1 means if I know the output, I definitely know the input. There's no choice. So if something is strictly monotonic on its entire domain, so that means it is always increasing or always decreasing, it has to be 1 to 1 and always has an inverse. So for example, a line that is not horizontal or vertical, so it's always increasing or decreasing, always has to have an inverse function. Okay, so anything like that can kind of go quicker to say it has an inverse. Okay, so the relationship between a function and its inverse, remember, was that f of f inverse equals x. So what we're going to do is we're going to actually kind of prove the formula for how we get the derivative of an inverse. Okay, so we're going to use that to do this. So what we're going to do first is we're going to let g equal f inverse of x. And by doing that, we're going to rewrite our problem as f of g of x, okay, equals x. And now we're going to take the derivative of both sides. So remember how we can write derivative, d dx of f of g of x. And then that's going to equal the derivative of x. Okay, so we have to do the derivative on both sides. So on the left, this is the chain rule. So we get f prime, so the derivative of f, leave the g of x alone, times the derivative of the inside, equals 1, because the derivative of x with respect to x, of course, is 1. So now what we're going to do is kind of solve this for g prime, because g prime, remember, equals g equals f inverse, so this is now f inverse prime. So g prime equals 1 over f prime of g of x. Now substituting back, okay, everything that we said, because we let g equals f inverse of x. So substituting back means this is f inverse of x prime is going to equal 1 over f prime of f inverse of x. Now, that's kind of a fancy little proof to that, okay, and a little fancy way to say this formula. Now, I like to just think of the formula in this way that we're going to talk about. If I want to find f inverse of 5 prime. So that's what this is asking. So they're telling me f of x is 4x minus 3, that f prime of 2 equals 4. Okay, they're giving me that information. We want to find the value of f inverse prime. So the formula says f inverse of 5 prime. The formula says that's 1 over f prime of f inverse of 5. Well, the way I like to think of that is when you say f inverse of 5, that's just the y value for f of x. Okay? So when you say f inverse of 5, remember we switch x and y. So that input would be the output for f of x. So since f of x equals 4x minus 3, the answer that goes here, or what I need there, is what is the x value. Because again, inverse switches x and y. So that means that this number is actually the y value for my original f of x. So I'm going to solve. When does 5 equal 4x minus 3? And I'm going to get 8 equals 4x, so x equals 2. So now I could go further and say 1 over f prime of 2, because I just figured out what f inverse of 5 is, and that answer is going to be 1 over 4, because they told me that f prime of 2 equals 4, and I would be finished. So the important information here, so some important information, is that when I see that I'm supposed to do f inverse prime, or I'm going to do f inverse of something prime, so I'm going to do the derivative. I just think it's 1 over normal function f prime at the x value, or the y value, because, or at the x value, that this is the y value, that 5, and I just have to find the x value that goes with it, and I need to know the derivative there of the regular function. And the reason this can be really helpful is sometimes it's hard to find, or we can't even really very easily at all find the inverse function. And so if I don't actually ever have to know what the inverse function is. Notice we never found the inverse. All we did was find one point that we have. But the point on here, the point is 2, 5, which means for f inverse, the point was 5, 2. And so that's the key of what I needed to know. I just needed to know, I think of it like this was the y value for f, and I need to plug in the x, okay, and do 1 over f prime of that. So this formula, I will say, is something that I would write down. And this would be one of those formulas that I would write down at the end of my composition book. So I would write this down as something I want to look at the day of the test, okay? Because it's going to be hard to remember it if we don't put it there and study the day of the test. It's not going to come up very often, okay? So sometimes I even skip the whole thing and don't even do it till the end, but we're covering it now, so the key is, what I would do is I would write this formula down. I'd probably write f inverse in there instead of that. But basically, g is the inverse. So this is f inverse of x prime. That's this formula, okay? And where this is f inverse. So steps for solving it. And this is another thing you could put on a page in your composition book so that you knew to study this, and even put a post-it note tab and put a little note on there that says study this right before the test, because you're right before the AP test, because you're not going to probably remember it. But it's not something to study constantly because it's just not going to come up that often. So basically, we simply, to find g prime of b, so in other words, the derivative of the inverse, we find f prime, because that's all we need. If you're given b only, so you're only given the y value, then you'll have to find the x that goes with it, and then evaluate f prime at that, and then the derivative is 1 over that value, and that's it, okay? So this is the actual formula, okay? But again, practice it a bunch, and mostly it will come up later. We'll talk about it a lot later. So we're going to do one example, and then we're going to do some derivatives of other bases, and we'll talk more about this and review this more in class. So we want to find g prime of -1, where g of x, we're told, is the inverse of f. So what you can do to help yourself, if you want to find that, is you could kind of fill in this table for the way the points would be. So if the point is 2, 5 for x, f of x, for g of x, it would be 5, 2. And so on. So this would be -1, 3, and this would be 4, -1. So they're simply switched. You switch x and y. And then we can find the answer for g prime of -1 by noting it will be 1 over f prime of g of -1. Well, g of -1 is going to be 3. So it's f prime of 3. And again, the way I think of it is, to do the derivative of the inverse, I simply want to do 1 over f prime at the x value, that what they're giving me is the y, so I want to do it at that x value. So it's going to be 1 over f prime of 3, which is just going to be -1 over 4, because you get 1 over -4, because that's f prime. So I never even had to know the values of anything else. Okay, I only had to know that. So I'm not going to fill in the whole g prime of everything. We're just doing the g prime of -1 is fine. Okay, and then we're going to talk about this continuity and stuff. We're going to do this a little bit later, so we'll do this in class. And so now let's talk about derivatives of other bases. So here are formulas that are on your formula sheets that you have for derivatives. So now these are fair game for a formula quiz. So, and it's simply the derivatives of other bases other than e for logs and for exponentials. And so it's really simple. These two are just with the chain rule in them. So these are the sort of main formulas, and the chain rule always applies. So anytime that isn't plain x, you're always going to take the answer times du dx. And notice that this and this always have to match. That's the most common mistake students will make on formula quizzes or on doing formulas, is they'll keep writing x, or they'll write u when in fact it's an x. So just because your formula quizzes or your formulas are written down with a u in them doesn't mean that you use u always. If this variable is an x, then you use an x in the formula, okay? So you do have to be able to distinguish that. But you'll notice that the formulas are very similar. The derivative of a to the x is still an exponential. You rewrite it. It's a to the x. The difference is you just have to multiply by ln of a. So whatever the base is. So for example, if you're doing derivative of, and we'll do this on the first one, first example, 3 to the x. So if we're going to do dy dx, do the derivative, just like any other exponential, so just like e to the x, you're just going to rewrite 3 to the x. But then you're just going to take the answer times ln of 3. That's it. Only difference. So that's all you have to remember. If we do b, the difference here is the inside is not plain x, so you have to do the chain rule, but we always have to do the chain rule regardless. So exponential, you rewrite it, that's the basic formula, times, because this is not e, it's times ln of 4, and because this is not plain x, it's times its derivative. Okay, and there you go. And that's the answer. You don't really need to rewrite it. There isn't really a good way to rewrite a lot of these, so you're good to go on that. Okay, now you might have difficulties matching because of exponential rules and log rules, but you're going to worry about those when your answers don't match, and then we'll figure out some things that we could do. All right, so here's again another exponential. So basic exponential rules say rewrite it. And then because this isn't e, I do times ln of 5. And then because this isn't x, I do times its derivative. And I'm done. And so I'm not even going to do d. We can save that for class. All right, so logs. So again, the formula for logs is basically the same as the formula for the other logs. The only difference is you have times ln of a in the bottom. Otherwise, it's exactly the same thing. It's du over u. So dy dx equals, it's a log. So logs are always going to be the derivative of the inside, which in this case is x, over the inside. Only difference, this is log base 5, so I have to do times ln of 5 out front here on the bottom. And that's it. So not a huge difference, just got to be careful to pay attention to the formulas. And this can be, of course, written 1 over x ln of 5. That's normally how we would write that with an ln, but it doesn't matter as long as you get to the point where you can match. All right, so again, doing my derivative, I say to myself, this is a log. So basic formula for derivatives of logs is to do the derivative of the inside, which is sine x, over the inside. But then because this isn't ln, so it's not base e, I just have to multiply the bottom by ln of 3. And that's it. That's how easy it is. And that's all we're doing, okay? So here, let's do one more example, and then we can save the other one for class. Let's do this one again. So again, main function is log. So derivatives of logs are going to be derivative of the inside. So here's the inside. So derivative of x is 1. Derivative of 3 to the x, well, it's an exponential, so it's 3 to the x. But then because it's not e, it's times ln of 3. And then this is a log, so it's derivative of the inside on top, which I just did, over the inside. But then because this isn't log base e, which is ln, this base, remember, is 10, because when there's not 1 written, it's 10. I got to multiply that answer times ln of 10 on the bottom there. Okay, so again, it's just practice. You need to do the homework so that you get that work in. So let's just do this example, and then I think that's all we're going to do for this video, and then we'll do the rest of the examples in class. So example 8 here, find an equation of a tangent line where x equals 2. So remember, as soon as something says tangent line, you're thinking, I got to find the slope, so I got to find f prime. So f of x is 6 to the x. It's an exponential, so its derivative is to rewrite it, because an exponential, it's just the same function, but because it's not e, it's times ln of the base, which is ln of 6. So that's f prime of x. I need to find the derivative, though, at 2, because I need the slope there. So that's going to be 6 squared times ln of 6, which is going to be 36 ln of 6. And that's just the slope, and you're just stuck with it. Do not even think about changing that to a decimal or anything. That's what I got. That's what it is. And then I also need a point, so I'm going to have to find f of 2, which is 6 squared, which would be 36. So now I have my point and my slope, so I can then write my tangent line. So always, again, identify what you're doing. So my tangent line is y minus the y, which we just found was 36, equals your slope, which is 36 ln of 6, times x minus the x, which was 2. And I'm done. So don't get stressed out about problems that have weird numbers in them and stuff. 36 ln of 6 is just a number. That's the answer, okay? So that's what we get. All right, so anything else that we're going to do on the notes, we'll do in class. So that's it for this video.